Here's a map I pulled off of Google Maps. You are right here and want to know how to get to one of the other intersections in the least amount of time. I'm going to clean this map up a little bit. Now I'm going to add vertices at the intersections, and then the streets become edges. Now we have a weighted connected graph, though we don't yet know the weight of the edges. We are going to use Dijkstra's algorithm to find the shortest path from our vertex B to all the other vertices. To start out, we label B with 0 and the others with infinity. It takes us 0 seconds to get to where we are now. But while it won't take an infinite amount of time of seconds to get to the other vertices as long as they're connected, we do this to show that we don't know yet what the actual travel time will be. Every iteration of this algorithm, we start by adding the lowest valued vertex to our cloud, signifying that there is no shorter path to get to this vertex. Since we're already at B, there is no shorter way to get here, so it's added to the cloud. Once a vertex has been added to the cloud, we update all of its adjacent vertices by adding its value and the weight of the edge and seeing if that is lower than the current value of the vertex. If it is, we replace it. The order we do this in does not matter. So our current value is 0, and this edge has a weight of 27. So we update A's label to be 27. I'm also highlighting the edges that are our current shortest path. Updating the labels like this is known as relaxing the edge. When we relax edge BA, we try to reduce its value by choosing the shortest path, either its current shortest path, which was originally infinity, or the path taking edge BA. Now we can also relax the other edges. 0 plus 28 will give us 28, so we update C to be 28, since it is less than infinity. Going from B to A along the top path, we have a weight of 48, which is greater than the 27 we saw before. This is not shorter, so I will not update vertex A, and I will mark this edge as dotted to signify that it isn't the shortest path. Once we have visited all of our vertex's incident edges, we can add a new vertex to the cloud. We will take the next lowest vertex, which will be A. We repeat the procedure on all unvisited edges. Edge AE adds an additional 9 seconds, so we add 27 plus 9 and update E's label to be 36. The process of adding the lowest vertex and updating adjacent vertices continues until all of our vertices are in our cloud. Here we find that going from E to I would add 34 seconds onto the already 36 seconds, resulting in 70 seconds, which is faster than our current time for I. So we update the label and change the edges to reflect our current shortest path. D doesn't have any unvisited incident edges, so we simply add the next vertex to the cloud. We are getting closer to the conclusion of this algorithm, and now have one vertex remaining that has not been added to the cloud. While very close, traveling to J via H ends up being a second shorter than traveling to J via I. We now add J to the cloud. J has no unvisited edges, and there are no remaining vertices, so we are finished. Each vertex's label has been updated with the shortest time it would take to reach when starting from vertex B. Should also notice that the highlighted edges forms a spanning tree of shortest paths. This concludes my video for Dijkstra's algorithm.